Very good evening to all of you. I am Phani Krishna, faculty of AS Engineering Academy. Today in this live session, I will be discussing about preparation strategy for all those students who are appearing for GATE exam as well as ESC exam, Engineering Services exam, and also some important concepts of my subject, that is electronic measurements. Okay, so please understand, before starting the session now, I want to clarify 2 points. First point is, this measurement subject is there in the syllabus for GATE EEE students and as well as GATE instrumentation students. It is not there for GATE EC. This measurement subject is there now only for EEE students as well as instrumentation students. For EC students, it is not there. Whereas for EC students, it is there in ESC exam. In ESC exam, no, Engineering Services exam, this measurement subject is there for EC students as well as EEE students, right? Normally for GATE exam, it is not there for EC. Otherwise, it is required, right? Most scoring subject in recent paper, no, they give many questions, conventional questions as well as objective questions. That is one point. Another point is the actual title of the subject is measurements we say, but actual title of the subject is electrical and electronic measurements. So in electrical measurements, no, you will study about the details of electromechanical instruments, like what? Like PMMC meter, moving iron meter, electrodynamometer, or EMMC, what you call as, or electrostatic meter. These are all the meters which are known as electromechanical meters, or you call them as conventional meters. You study about those meters where electric current is translated into mechanical deflection of the pointer in electrical measurements. And also bridges, resistance measurement, power energy measurement, all those measurements you will study errors in electrical measurements. So electrical measurements is a study of, it is regarding about a study of electromechanical instruments. The same manner, electronic measurements is about a study of electronic instruments, electronic meters. But what electronic meters? So many electronic meters are there, please understand. So many electronic instruments are there. All that is not required. Maybe in engineering, no, in a BTech exam, maybe in third year or final year, based on the university, depending upon the university, you people might have learned about one subject, no, electronic instrumentation or EMI, which you call. So many electronic meters to study, all that is not required. I observed, no, all 20 to 25 year previous year question papers I observed, and based on that, no, I prepared few topics based on the syllabus, right? Whatever be the way they mention in GATE exam syllabus or ESC exam syllabus or any PSU syllabus, based on all those previous year question papers, no, I prepared. These are the topics. Let's start with this topics of the TMI, right? One is cathode ray oscilloscope, which you call it as in short form CRO. Later I will elaborate. First you will see what is the table of contents. One is CRO. Another one is electronic voltmeters. You see here there is a pointer deflecting over a calibrated scale, now voltage calibrated scale. So this is a analog electronic voltmeter. Actually AC moving coil type I mentioned. That is a rectifier type instruments. Later I will elaborate. And also another one is digital voltmeters. You see this display is a 7 segmented digital display. 18088 is being displayed now. Actually this diagram, this figure is of digital multimeter, right? This is a electronic voltmeter analog type. This is also electronic voltmeter digital, right? And also Q meter, that is quality factor meter. These are the topics you are supposed to learn. That you are preparing for GATE exam or ESC exam or PSU exam, any state level PSU exam. Electronic measurements means these are the topics you are supposed to study. Apart from this, no, there are so many other meters, please, like a distortion factor meter, a distortion analyzer, wave analyzer, right? So many meters are there, all that is not required. Maybe 1 or 2 questions, rarely they will ask about a spectrum analyzer, something like that. But no, these are the main topics that you are supposed to learn, right? So one by one I will elaborate what you are supposed, that is what preparation strategy. Preparation strategy not exactly for a GATE exam, preparation strategy regarding this, my subject please, electronic measurements. So let's start with the first topic, that is cathode ray oscilloscope. You see here, this is the cathode ray oscilloscope. single channel analog CRO or dual trace CRO, dual channel CRO. Where you have seen this cathode ray oscilloscope, you people might have used in the first year as well as second year labs. Some lab you might have used. At that time, now you see it is visible now here 2 cycles, 2¼ cycle of a sine wave is displayed. What you people did as a student in the lab session, you carried out measurements, right? Possibly without even knowing about what is there inside of a cathode ray oscilloscope, you might have used a CRO, that's CRO, and you carried out measurements. You attended some lab sessions, you have used a probe and all that. But from a questioning point of view, objective question point, exam point of view, what you are supposed to learn? You need to start with the block diagram, please. Circuit diagram. What is there inside the CRO? Inside, this is what actually the screen. The user interface is nothing but the screen where you will observe image, steady image of an unknown signal you will observe. What is there behind the screen, inside this box? These are all various controls, as you can see. Various control, volt per due, time per due, focus control, intensity control, position control, different controls will be there. So what is there inside this box? That block diagram you need to study. The circuit diagram you need to study. Functional building blocks, basic building blocks, whatever building blocks that are there in the CRO that you need to learn. Let me just mention. One is a vertical section, another one is a horizontal section, another one is a display section, which you normally call it as a CRT, cathode tube, and also power supply section. All these 3 sections, vertical section, horizontal section, display section, all these sections require power, right? Some circuits require high voltage requirements, some circuits will have low voltage requirements. All that will be fulfilled by this power supply section. So these sections you need to learn. What is there inside vertical section? Vertical amplifier is there. What is the purpose of vertical amplifier? What are the control that is going to adjust the gain of the vertical amplifier? Sensitivity means what? Sensitivity of the vertical amplifier, how to change? What is a delay line, right? Some questions may be there on the delay line, you people might have seen. What is there inside of this horizontal section? What is time per due control? What is sweep generator? What is a trigger circuit? All those individual blocks you need to learn. And also mainly that CRT, which I am calling it as a display section, is actually CRT. CRT stands for cathode ray tube, that is known as heart of the CRT. You need to learn about CRT. This screen you are observing now, this fluorescent screen is there at one extreme end of that CRT. Those building blocks you need to study. But study means what? Not the way you learned in engineering. There you use it to learn, use to practice the circuit diagram of the CRO. That is not required here. Until unless you are appearing for ES exam. If you are appearing for GATE exam, just go through the building blocks of that block diagram of that CRO. That is enough. You need not practice how to draw that circuit diagram. Then what are the modes of operation of the CRO? Let me mention there are 2 modes. One is known as YT mode. You see, right now the CRO is being operated in YT mode, as you can see. That Y signal is being displayed. That is a sine wave. Number of cycles of signal is going to be displayed in YT mode. And another one is XY mode. Those 2 modes, these 2 modes. This is known as a sweep mode. You can also call this YT mode also is going to be called as a sweep mode. So 2 modes are there. In that circuit diagram, you will understand. While learning about the block diagram, you will understand what is YT mode, what is XY mode. In YT mode, images, what kind of images are going to be displayed that you need to learn. In XY mode, what kind of images are going to be displayed that you need to learn. Right? YT plots will be displayed in YT mode, which is also called as, let me mention here, sweep mode. Sweep signal is a reference signal used for working of the CRO. So YT plots means what? Right now you are observing now that sine wave displayed on the screen. Flicker free, not a jumble, not a moving display. You should vary all these controls properly. Already you people might have done in order to get a steady image of the signal. Then only you can carry out. So that signal is going to be called as a YT plot. Just I am drawing the screen, for example, 1 cycle, 2 cycle and quarter cycle, as you can see there. That 2/4 cycle is displayed on the screen of the CRO. While observing that image, you need to carry out measurements. That is what image of the unknown signal. When you connect the CRO into the test circuit, some unknown signal you are measuring, image of that unknown signal is displayed on the screen. So what commonly people assume, I have seen in the class sessions, people think they visualized, they observed sine wave on the screen. they think that a sine wave is a reference signal. It is not like that. Inside, for the working of the CRO, a sawtooth signal, which you can also call it as a sweep signal, is being generated in the horizontal section and used in YT mode to feed the X input of the CRT. So sine wave is not a reference signal, please. What is sine wave? You did not, while observing that image of the unknown signal, you as a user carried out measurement. So that is unknown signal, whose image you are seeing. Not only sine wave, it may be in one question I have observed, in one question later we will see something like a square wave displayed on the screen, or a triangular wave displayed on the screen. You see, triangular wave displayed on the screen. Maybe one cycle, more than one cycle, number of cycles. Or AC plus DC also, it need not be exactly at center. AC A plus B sin omega t displayed on the screen. These are all known as YT plots, please. Y versus T, like you draw on a graph sheet. Voltage versus time. This is what? This is a time domain representation of the unknown signal which you want to measure. Frequency domain representation will be presented by another special electronic instrument that is known as spectrum analyzer. That frequency spectrum will be present, not this one. So while observing these images, any one of those images, you are going to carry out measurements. What kind of measurements? You can carry out measurement. Peak to peak voltage you can measure. Peak voltage you can measure. Once you get peak voltage, you can measure RMS voltage. Anyway, here DC voltage is 0, right, for alternating signal. But if it is a shifted waveform, you can also carry out measurement of average value of that signal. You can also measure frequency of that signal. You can measure time period of the signal. You can measure rise time. You can measure fall time. On paper, if it is a pulse waveform, you can calculate percentage tilt. All these measurements can be carried out using, right, image of the unknown signal. Questions will be on this one. Right? They will give you, later will solve, they will give you some waveform, they will give you some controls here, volt per due, time per due controls. They will ask you what is the RMS voltage of the signal, what is the frequency of the signal. Some other kind of question also. They will ask you how many number of cycles of the signal displayed on the screen of the CRO while giving input to the CRO and some control setting values. So mainly this is what our focus, please. To start, to understand this, you need to start with this block diagram. General idea of the block diagram we should have. Then the other kind of images that can be displayed on the screen is known as XY plots. XY plots are also very popularly known as lysagious figures. These lysagious figures are displayed in which mode? In XY mode. I just mentioned YT mode is one mode of operation. XY mode is another mode of operation. What do you mean by lysagious figure? Something like a circle displayed on the screen. Something like a diagonal line displayed on the screen. Something like a ellipse displayed on the screen. Or something like a parabola displayed on the screen. So many lysagious figures are there. Some standard lysagious figures you need to learn. Not all the lysagious figures. Infinite number of figures you need not learn. Some finite number, standard lysagious figures you need to learn. But point is, while observing these lysagious figures, you cannot carry out peak-to-peak voltage measurements. Only two measurements can be carried out. Measurements you want to carry out using lysagious figures. One is known as frequency measurements. One measurement is frequency, you can measure unknown frequency, and also phase difference between X and Y input signals you can measure. These are the two measurements which can be carried out using lysagious figures. Questions will be on that. They will give you a circle and they will ask you what is the phase difference between X and Y input signals. Or they will give you X input signal and Y input signal, and question will be on what is the type of the image going to be displayed on the screen of the CRO. These are the main topic, please. In CRO means, so you have to learn YT plot and XY plot. And some additional points about something like probes. You people have used probe now. Without using a probe, you cannot connect CRO into the test circuit. That is a special connecting medium. What is an active probe? What is a passive probe? Mainly you need to focus on passive probe, please. What is a passive probe? What is a 10:1 attenuation probe? When you connect a CRO into the test circuit with the help of a 10:1 probe, what is the effective resistance at the probe tip? What is the effective capacitance at the probe tip? Usage. You see what I wrote here? Design and usage you need to learn. Suppose if this is the probe, assume, then 10:1 probe, they will ask you what is the probe resistance, what is the probe capacitance while designing a 10:1 probe to be used along with this CRO. They will give you the input impedance of the CRO and they will ask you to design a 10:1 attenuation probe. What is the probe resistance and what is the probe capacitance? That is what design. Usage means what? You have used CRO along with probe now. You connected CRO into the test circuit. They will give you the CRO input impedance and they will ask you what is the effective resistance at the probe tip. They mention about the type of the probe, 10:1 probe, something like that. 10:1 probe, attenuation probe, something, some passive probe information they will give, and they will ask you what is the effective resistance at the probe tip. Later we will see one such question. Some formulas please, RP formula, probe resistance formula, probe capacitance formula, effective resistance formula, effective capacitance formula, that you need to learn. And special CROs. Special CROs, rarely, once in gate exam, I have seen one question on dual trace CRO. They asked about the multiplexer switching speed in comparison with the sweep rate. Rarely they will ask you. So just briefly, you go through. Whatever you learn actually is about whatever I mentioned in the beginning as block diagram is a single channel analog CRO that you need to learn. But special CRO is also going to be there. Dual trace CRO, dual beam CRO, sampling oscilloscope will be there, storage oscilloscope will be there. Just to go through, just to look at the block diagram, just to go through some features, important features, right? That is enough, more than enough. Rarely they will ask. And corresponding problems, we will see in the important concepts now. I will explain about the concept of some concepts through problems. So this is what, from my observation as a faculty, right? I observed 20 to 25 year previous year question papers. Based on that I prepared to cover maybe 1 or 2 points may not be there, but to cover all that area, right? But not the way you learn in engineering, please. You learn about different circuits, even vertical amplifier circuit, that delay line, lumped parameter delay line, distributed parameter, so much of data will be there, not in that point of view, that is different. If you want to answer some conventional questions, subjective questions, then that is required, but not here, right? Then the next topic is electronic voltmeters. In short form, we call them as EVMs. You see here, I gave you AC moving coil type. AC moving coil type means is actually a rectifier type voltmeter, whatever I mentioned. Here you can see this diode symbol is there, V, and this symbol of AC symbol is there. Moving coil instrument, as all of you know, it is for what? PMMC, for a DC inputs. It is a DC meter, not for AC inputs. By adding a rectifier, maybe a full wave rectifier or a half wave rectifier, you can make the moving coil instrument to be used for AC inputs, right? That is what actually the design of rectifier instruments. So this is an analog voltmeter, please. But point is, you study about conventional meters, electromechanical meters, PMMC, moving errand, dynamometer, all that you will study now. What is PMMC? It is a conventional DC voltmeter. What is moving errand and dynamometer? They are conventional AC voltmeters. So question is, when conventional DC meter and conventional AC meter are available, what is the need for a electronic DC voltmeter and electronic AC voltmeter? That you need to start with. You need to understand why there is a need for an electronic voltmeter. Then means what? Why there is a need in the sense what? There are some limitations for PMMC voltmeter, conventional DC voltmeter. There are some limitations for conventional AC voltmeter. To overcome those limitations, they designed these electronic voltmeters. Still analog only. So you need to study why we require electronic voltmeters, and then what are the advantages of electronic voltmeters over conventional voltmeters. What I mean by conventional voltmeters, that PMMC, moving errand, etc. 4 types will be there, 4 types of analog electronic voltmeters. One is amplifier type, DC electronic voltmeter, rectifier type, AC electronic voltmeter, peak responding type, or simply people call peak type, AC electronic voltmeter, and also thermocouple type AC electronic. Briefly, for gate exam it is not much important. Please. Gate instrumentation it is important. Gate AAA I am saying it is not much important. But when you are studying about electronic meters, no basic idea you should have. It is better because when you appear for some ESC exam or PSC exam, you will find questions on electronic voltmeter. For gate instrumentation students, rectifier voltmeter is important. I have seen questions, 1 or 2 questions on thermocouple voltmeter. Some 1 mark objective questions are there in ESC paper, previous ESC paper on amplifier type DC electronic voltmeter. They don't mention amplifier type, they mention electronic voltmeter. They question you on the sensitivity, they question you on input impedance in comparison with this conventional voltmeter. So gate exam, it is not much important, right? But for gate instrumentation people, it is important, not for gate triple E, right? Just go through, one statement will be there now. When you are appearing for gate exam later, you may want to write some PSC exam also, right? Just go through and corresponding problems, right? Problems in the sense, no, I observe, no, in gate instrumentation papers, you will find many questions, no, many questions are there on full wave rectifier, full wave bridge rectifier type AC voltmeter. So just go through. And yes, this is what one of the most important topics of electronic measurements, digital voltmeters. Whatever diagram I gave is actually digital multimeter, right? Because I want to show this, this display I wanted to concentrate. So this is actually a digital multimeter diagram. You people already might have used a digital multimeter in the lab sessions, no? Without even knowing what is there inside of a digital multimeter. Is it not? When I ask in class sessions, no, analog meter is used for measuring analog signals. Then I ask, digital meters are used for what? People say digital signal. Some people say analog and digital signals. It is not like that. Either analog voltmeter, just now you have seen that diagram, or a digital voltmeter, both are meant for measuring analog signal only. Where in an analog voltmeter, measured value will be displayed on an analog indicator, pointer deflecting over a calibrated scale. In a digital voltmeter, you see what is there here? This is the 7-segment digital display. Our main concentration will be on this display place. So you need to start with the functional working of a digital voltmeter. So what is there inside this box? You have used a digital voltmeter without even knowing about the operation inside. What is there inside? A to D converter is there, attenuator is there, that range switch means what? Decimal point select switch. Here you see decimal points are there now, 2, 20, 200, these are the decimal points now. So what do you mean by those decimal points? Decimal point select switch will be there, which is ganged with the range switch. So that point of view you need to learn. Again I am saying, you need not practice those block diagrams please. Just understand the design. For solving the problems, you need to understand the internal circuit operation. Then about dual slope integrating ADC features. Please understand, this is the dual slope integrating ADC is the most preferred ADC used in the design of the digital meters. The design ramp type DVM also will be there, other DVMs also will be there, but most preferred ADC is dual slope integrating ADC. So where you will learn about ADCs, either EC students or triple E students or instrumentation students, you will learn in gate exam where you will learn in digital electronics, you will learn all A to D converters. Focus on dual slope integrating ADC. One voltage to time converter will be there, followed by timer counter. Whatever be the way the faculty explains from instrumentation point of view. First section is voltage to time converter. Second section is electronic timer. That you see. Focus on that. Learn the formulas of dual slope integrating ADC. Because while solving some questions on DVMs, no, they can question you on dual slope integrating. It is integrating type. What are the features? What is the input impedance of this ADC? What is noise rejection of this ADC? What is the stability? How it is used in a normal measuring environment and noisy measuring environment? Some questions will be there based on that. And also, what are advantages of DVMs over AVMs? Digital voltmeter over analog voltmeter. Analog voltmeter means conventional voltmeter again. Previously, you have seen analog electronic voltmeter. This is a digital electronic voltmeter. So, what is the advantage of a digital voltmeter or PMMC voltmeter? That you need to learn. What is the input impedance? What is resolution? How is the loading effects? Loading error, how is loading error? Is it reduced or what? What about frictional errors? What about observational errors? Right? Ranging, auto ranging, over ranging, all those advantages, just you study. You need not present please. In a gate exam, there are going to be objective questions now, right? And digital readout. What do you mean by full digit? You see here, 1, 2, 3. These 3 digits are full digits please. Each digit can display anywhere from 0 to 9. This one, the MSD, most significant digit, is known as half digit. Right now you can show it is showing 1. What is a half digit? What is 3 by 4 digit? What is a full digit? What a full digit can display? Half digit can display, 3 by 4 digit can display. And then what is the features of n digit DVM, n and a half digit DVM. N in the sense you learn for 3 digit DVM, 3 and a half digit DVM. Whatever you learn for 3-digit DVM can be applied for 4-digit DVM, 6-digit DVM. Whatever you learn for 3.5-digit DVM, you can apply it for 4.5-digit DVM, 6.5-digit DVM. Specifications of the DVMs, that also you need to, formulas will be there, resolution, what is sensitivity, how is the input impedance, right? All those formulas now you need to learn. What is best resolution, what is maximum voltage, what is count range, what is scale, and digital multimeter. This is what actually the diagram of a digital multimeter, because in the question now when you see they mention 3.5-digit digital multimeter. They will give some AC signal. This digital multimeter will be kept in AC voltage range. Either they mention or not in a problem. So you need to understand what is the meaning of that. And corresponding problems. Few problems we will see in the concepts piece. Okay. Then finally concluding with the Q meter, quality factor meter. People think it is not much important, but you see in this year ESC paper, they asked a 20-mark question, subjective question. Explain the working of a practical Q meter and applications of Q meter. Learn about that Q meter, basic applications of measurements, what you can measure using Q meter. You can easily answer that question, please. So what you need to learn, you need to start with the properties of a RLC circuit. Why I should learn about properties of RLC circuit? So this is a Q meter. Principle of working is nothing but series resonance. Q meter is basically a series RLC circuit at resonance. So start with the properties of a series RLC circuit, not that resonance curve and all that. Anyway, you will study that in networks. Is it? And about Q meter circuit, this is what I gave. Q meter circuit diagram I gave. How to operate. What is the meaning of this tuning capacitor? This tuning capacitor, resonating capacitor, variable capacitor, working of this. What are the various connections, please? Actually, 3 types of connections are there. Let me mention here. One is known as a direct connection. Another one is known as a series connection. Another one is known as a shunt connection. Some people also call that as parallel connection. Please focus on direct connection, please. Most of the times, they question you on direct connection, right? And what measurements you can carry out using direct connection. This is what the unknown coil, as you can see, as placed in the socket of the Q meter. What measurements you can carry out? Q measurement of this coil. This is CD measurement. Mainly this is important, please. CD measurement is important. Most of the times, no, the question on CD measurement. CD means what? Distributed capacitance of the coil or self-capacitance of the coil. There will be some tuning process. You need to carry out the tuning process and measure that CD. And also this L measurement, self-inductance measurement. And also resistance measurement. And what are the errors? One error source is this RSH, another error source is this CD, right? You need to learn about what are the formulas for percentage error in Q measurement due to the shunt resistance, insertion resistance. What is the percentage error due to CD and corresponding problems? What problems? So these are the topics you need to focus, please. If you are preparing for GATE exam or for GATE exam, that amplifier, rectifier, voltmeters are not much important, but just go through, right? For instrumentation people, some extra topics also you need to learn. In CRO, you need to learn instrumentation people. CRO, you need to learn about triggering and problems on triggering. 2008 and 9, I think 7, 8 somewhere they gave 2 questions, one after another year, right? And on electronic timer counter, you need to learn, GATE instrumentation people. What is a timer counter? What is a timer mode of operation? What is counter mode of operation? What is a digital frequency meter? What are applications of timer? Some extra topics you need to learn, right? What about the study materials? Obviously, in the class, no, I will provide the notes as a faculty while teaching this subject, electronic measurements. I will provide all the points. I will provide circuit diagrams. So you should understand, we prepare point. For example, you take myself, no, I prepared points after observing solutions for various questions in ESC papers. No, 1 more questions will be there. Right? While observing those questions, no, I prepared some points. Those points as a part of the subject I will give. So if you go through those points, no, most of the questions are solved in ESC papers. And after going through that notes, listening to my class, you prepare your own notes, definitely. All these are block diagrams. You cannot again prepare short notes, means not block diagrams. Who will ask you to try block diagram? GATE exam. ESC subject to conventional questions they will ask you, but not in GATE exam, right? What is formula for Q? What is formula for L? What is resolution of a DVM formula? What is sensitivity formula, right? Briefly, half digit means what? Full digit means what? 3/4 digit means what? What is the deflection sensitivity formula in CRO? What is the deflection factor formula CRO? Peak voltage measurement, frequency measurement. Those measurement formulas will be there. Many formulas will be there. All those formulas you try to prepare short notes. And whenever it is required, you go through. And also definitely you need to follow some textbooks, right? According to your requirements, according to your time, whatever based on the time, right? Time constraints will be there. At maximum, if you are a student of ACE Institute, please go through the material notes provided by, class notes provided by the faculties. But you want to go through any textbook for measurements, I am providing here. You see, one is A.K. Sahani, very popular, electrical and electronic measurements. You see, electrical and electronic measurements. You want to only focus on electronic measurements and instrumentation, please go through David Bell. This is actually the textbook I follow. Based on this only, I prepared the CRO notes, DVM's notes, Q-meter notes, AVM's notes, right? Based on this only. From the beginning, I follow this only. And then one more is there, H.S. Kalsi, simplified detailed explanation will be there, right? So these are the books. If you have any other textbook, you please go through. So this is how you are supposed to prepare for GATE exam regarding electronic measurements. Let's start with some concepts I want to explain through questions. All the concepts within this 1 hour session I cannot give now. So some questions, previous GATE and IES and some model questions I will try to solve. While solving those questions, I will give you the concepts, right? Let's start with the question on CR. You see, a CRO screen has 10 divisions on the horizontal scale. If a voltage signal 5 sin 314t plus 45 degree is examined with a line setting of 5 millisecond per division, then the number of cycles of the signal displayed on the screen will be 0.5 cycle, 2.5 cycle, 5 cycle, 10 cycle. When you see this kind of question, you should have some information, some formulas you are supposed to know. I cannot give you how you got those formulas now in this session. Directly I will tell you the formula and I will use the formula. Observe what is the given data. CRO screen has 10 divisions on the horizontal scale, please. This is what horizontal scale. This horizontal scale is divided into 10 divisions. What is the voltage signal you are sensing that is applied to the vertical input? 5 sin 314t plus 45. What is the line setting? 5 millisecond per div. They are asking you the number of cycles. So let me write what is that given data. Given data I am writing. Total, how many horizontal divisions are there? 10 horizontal divisions are there. X divisions on the horizontal scale. Total 10 horizontal divisions are there. What is one more parameter given? Voltage signal that you are sensing, that unknown signal you are sensing is 5 sin 314t plus 45. 5 sin 314t plus 45 degrees. So please understand what is this 5, what is the meaning of that 5 volts? Peak voltage is given to you. Actually it is unknown signal, strictly speaking. In the lab session, that signal they mention here is unknown signal. In lab you don't know, you have to measure, strictly speaking, right? So what is 314t? 314t is frequency of the signal. 2 pi ft is 314t. 314t is not frequency. 314t means 2 pi ft. So what is the frequency of the signal? All of you know it is 50 hertz. That is the signal. What is one more parameter given? Line setting is, you call it as line setting or you call it as a time-based setting, sweep setting. Time-based setting or sweep setting or line setting is how much? What is that value given? 5 millisecond per division. 5 milliseconds are required to cross one division. This is the data given. Always you write down what is the data given to you. Then they are asking you not about this signal where parameters are known to you. They are asking you about the number of cycles. So what is the formula for number of cycles? Number of cycles is equal to sweep period by signal period. sweep signal is applied to X inputs, unknown signal is applied to Y inputs. Within the sweep period, whatever be the portion of the unknown signal is there, that will be displayed on the screen. How to calculate sweep period? You know, all of you know, total horizontal divisions multiplied by the time taken to cross each division. This screen, horizontal scale 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 divisions are there. Time taken to cross one division is 5 milliseconds. So to move from left side of the screen to the right side of the screen, how much time is taken? That is what actually sweep period. So total 10 divisions are there. Multiplied by, what is the time per div? 5 millisecond per division. That is what the formula for calculating the sweep period. Then what is the time period of the signal? Frequency of the signal is 50 Hz. So time period of the signal is 1 by 50 Hz. Right? So please calculate. What is this N? 10 horizontal divisions into 5 millisecond. Division gets cancelled out. This is 50 millisecond by 1 by 50 Hz, you know, 20 millisecond per cycle. 50 by 20 milliseconds will be cancelled out. 50 by 20 is 5 by 2 is 2.5 cycles of the unknown signal going to be displayed. This. You know what is the meaning of this? 1 cycle, 2 cycle and half cycle are there within this 1 cycle of the sweep period. Because of the sweep signal is applied, spot will move from left to right and back to left on the screen. Left to right, back to left. Trace, retrace. So during this trace, whatever be the number of cycles of the unknown signal applied to the Y input going to be displayed on the screen. So what is the answer? 2.5 cycles. In any other way you want to do, you do, right? That is up to you. That's the meaning of short notes now. You have a shortcut, right? You prepare use your own shortcut and try to calculate this. That is up to you. One more question. An oscilloscope is operated with a line setting of 0.5 millisecond per division and vertical setting of 100 millivolts per division. 2 cycles of sine wave is observed on the screen, which occupies 8.8 horizontal divisions and 4.6 vertical divisions. Then the RMS voltage and frequency of the sine wave respectively are. This is a model question actually. Those are the 4 options, please. 162.6 millivolts, 227 hertz. Voltage and the frequency are given. You can see in 2 options, same value. In these 2 options, same values. So when you read such question, no theory question, you please go through what is the data given to you. Time per div is given 0.5 millisecond per div. In the previous question, 5 millisecond per division. That is what actually setting value. And what is the vertical setting? 100 millivolts per division. That voltage required to move the electron beam, better say spot on the screen, by 1 division is 100 millivolts per division. The time required to move that spot on the screen by 1 division is 0.5 millisecond. That is the meaning. These are the front panel control settings. And how many cycles now you see? 2 cycles of sine wave. The previous question, no, they asked how many number of cycles are displayed. Now they gave you the number of cycles of signal displayed on the screen and how many divisions they are occupying. 8.8 horizontal divisions and 4.6 vertical divisions. All this is the data given. Let me write here what is the data given. Given data is what? One is a time per div. What is time per div? 0.5 millisecond per division. You are going to set this value 0.5 millisecond per division. And another one is volt per div. What is volt per div setting? 100 millivolts per division. 100 millivolts per division. What else is given? One more information is given. What is it? 2 cycles of sine wave is observed on the screen. This is 1 cycle. This is 1 more cycle. So actually n is equal to 2. Number of cycles of the signal displayed on the screen is 2. Occupying how many horizontal divisions? 8.8 horizontal divisions, right? And 4.6 vertical divisions. They are occupying 4.6 vertical divisions. This is what actually data given, you have to understand the data given to you. And what they are asking you, what is the RMS voltage and what is the frequency? There is a formula. This is what you did in the lab. Directly you don't calculate RMS voltage. When you see the steady image on the screen, you please count how many vertical divisions are occupied by the signal. Multiply it with the volt per div, that will give you peak to peak voltage. Half it, you will get peak voltage. Then use the formula for RMS. I am doing that here, you see. What is the peak to peak voltage? I am not writing the formula here. Peak to peak vertical divisions. How many vertical divisions are there? Peak to peak 4.6. Multiplied by the volt per div. What is volt per div? 100 millivolts per div. What is this value? 4.6 division into 100 millivolts per div is 460 millivolts. That is peak to peak voltage. So please calculate what is peak voltage and what is peak voltage? Half it. Peak to peak is 460 by 2 is peak voltage. What is that peak voltage? 230 millivolts. 230 millivolts. Question is not about peak voltage. Question is about RMS voltage. So what is RMS voltage? RMS voltage is, now here you see one point is, that depends upon the waveform being displayed. Ante kada? Sine wave displayed, VRMS is Vp by root 2. Square wave displayed, VRMS is Vp. Triangular waveform, VRMS is equal to Vm by root 3, Vp by root 3. So what is the waveform here being displayed? Sine wave is displayed. You got the peak voltage as 230 millivolts. So 230 millivolts by root 2. Please calculate 230 millivolts by root 2. You will get it as 162.63 millivolts. That is RMS voltage. What common mistake no people do? Common mistake what they do? They calculate this peak to peak voltage in hurry, they do by root 2. 460 by root 2 they will do. That is wrong. That is one mistake. Another mistake is they will calculate peak voltage, right, for any other waveform. Suppose in the question square waveform is given, but in general in the notes you will see VRMS is equal to Vp by root 2. They will use that formula. Because in the class session we just draw sinusoidal waveform only. That is the most preferred, that unknown signal, mostly encountered, not most preferred, mostly encountered unknown signal. So people use that formula for square wave, not like that. Depending upon the waveform you have to use, right? So that 162.63 is there in two options. So A and B options, I think. A and B options, it is there. So C and D are ruled out now. So you have to calculate the frequency, either 227 Hz or 455 Hz. So let's see. What is that formula for time period of the signal? First measure time period of the signal. What is the formula for time period of the signal? Time period of the signal can be calculated by the user while observing the steady image of the unknown signal. You have to get the steady image. You have to adjust that volt per div, you have to adjust the time per div, focus control, that intensity control, sharpen the beam, change the number of electrons, that is the intensity, brighten the image, adjust sensitivity, then only you will get a steady image. Flicker free image you don't get, jumble you will not get, you will get a steady image. What is the formula for time period of the signal? Count the number of horizontal divisions within one cycle. Whatever be the number of cycles given, you always count the number of horizontal divisions within one cycle, multiply it with the time per div. You will get the time period of the signal. Common mistake people do is, they will do this calculation, and for starting like this, because you don't draw this waveform, for explanation I have drawn, you go back and study, occupies 8.8 divisions, they multiply 8.8 divisions with 0.5 millisecond per div. That is wrong. 8.8 divisions with 0.5 millisecond. That is wrong. Why? 8.8 divisions are occupied by what? Occupying how many divisions? 8.8 divisions are occupied by 2 cycles, not by 1 cycle. So 8.8 divisions by 2 cycle you have to take. In hurry, if you just do 8.8 into 0.5, you will get wrong answer. So 8.8 in 0.5 means 1 by 2. So 8.8 by 2 is 4.4, by 2 is 2.2. It must be 2 cycles. You must be careful about this units please. 2.2 division gets cancelled out, millisecond per cycle. One cycle, 2.2 millisecond. Question is not about time period, question is about frequency. So what is the frequency of the signal? Frequency of the signal is 1 by time period of the signal. What is 1 by? 1 by 2.2 millisecond per cycle. So inverse no, cycle per second you will get. 1 by milli is 1000. 1000 by 2 is 500. More than 2.2 means it will be less than that. So obviously when you calculate, you will get 455 cycles per second. Cycles per second units are hertz. 455 hertz. That is the answer. 162.63 millivolts and 455 hertz is the answer. It is there. 455 hertz. So directly I am using the formulas, please. I cannot explain how you got that formula. I am trying it out, but this is not the stage, right, where I am supposed to give you the explanation for the formulas. Right. So one more question we will see. The time per due and volt per due, this is a gate question. Time per due and volt per due, axis of an oscilloscope have been erased. What do you mean by erased? They are the control settings, please. They are not given, right? A student connects like you, a student connects a 1 kilohertz, 5 volt peak to peak square wave calibration pulse to channel 1 of the scope and observes the screen to be as shown in the upper trace of the figure. This is the figure, please. You see, 2 traces are given here. Upper trace is this screen you see, so many divisions are there on the screen, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Horizontal divisions. 1, 2, 3, 4, 5, 6, 7, 8 vertical divisions. You, right, you as a student, you connected a calibration pulse and you got upper trace like this. They are giving the values of that upper trace, that 1 kilohertz and 5 volt peak to peak square wave is shown here. What is the frequency of this square wave? 1 kilohertz. Data is given to you. And what is the peak to peak voltage? Here to here is peak to peak is 5 volts. That is displayed on the channel 1. This is actually dual trace CRO. This is what actually dual trace CRO. An unknown signal is connected to channel 2. That is lower trace. You see, this is lower trace. What is this waveform? This waveform is a triangular waveform. If the time per due and volt per due on both channels are the same, then the peak to peak amplitude and period of the unknown signal are respectively, right? This is what actually given figure. Those are the values, please. 5 volt 1 millisecond, 5 volt 2 millisecond, 7.5 volt 2 millisecond, 10 volts 1 millisecond. So please understand what is the given data you observe. They are not giving you the time per due and volt per due. First question they gave 5 millisecond per due, time per due given. The second question they gave time per due as well as volt per due. Kada? 5 millisecond per due, 0.5 millisecond per due and 100 millivolts per due. Both are given. But here they are not given. You need to calculate them with the given data. What is given data? Waveforms are given here. You see, waveforms are given. This waveform and this waveform. They are occupying divisions, peak to peak divisions, horizontal divisions. So what I will do is, I will first observe this first statement, please. Observe the first statement. This is a gate question given. What is that first statement? Upper trace. The question, statement is about upper trace. They are telling you this is the upper trace, 1 kilohertz frequency, 5 volts peak to peak. How many cycles are displayed? On time, off time, 1 cycle, on, off, 2 cycle, and this is on half cycle, 2.5 cycles are displayed. So, I will start with the solution. First, I will mention about channel 1 display. Channel 1 display is upper trace, please. Channel 1 display is upper trace is of, there itself you can do, actually there itself, here itself, no, you can do calculations and all that. I don't have space here, so separately for explanation purpose, I am doing it, right. Channel 1 display is of known signal or unknown signal. Known signal, 1 kilohertz frequency is given, known signal, let's call it as signal 1. What is that signal actually? That signal is a symmetrical square wave signal. That is a square wave, please. Channel 1 displays upper trace is of known signal. What is known to you? In the question you can see now, this data is given. What is that? Frequency and peak to peak voltage. Peak to peak voltage of the signal 1 in the sense signal 1, channel 1 display is 5 volts, and frequency of the signal 1 is how much? 1 kilohertz. When frequency of the signal 1 is 1 kilohertz, what is the time period of that signal 1? 1 by 1 kilohertz. Time period and frequency are inversely proportional. 1 by frequency is time period is 1 millisecond. So this time period is 1 millisecond. This peak to peak voltage is 5 volts. So let me draw that, how it is there. It is on time, off time. That is actually enough. That is one cycle, that is one cycle, that is enough actually. Let me draw the remaining part as given. This is 1 cycle, 2 cycle and half cycle, is it not? That is what given. Why 2.5 cycles are displayed? Within the sweep signal, right? 2.5 cycles are there. In the first question we have done, within that 1 cycle of the sweep, 2.5 cycles of the square wave are there. So this n is 2.5, in this n1 you can say 2.5 cycles. How many horizontal divisions are occupied for 1 cycle, that you need to see, and how many vertical divisions are occupied from peak to peak. That what actually you have to observe. There itself you can write. Here 2 divisions, 1 and 2. Here how many? 1, 2, 3, 4. 4 divisions are occupied. So here to here, 4 horizontal divisions are occupied. Here 2 vertical divisions are occupied. That is what given data. All this is given to you. What about volt per due? Not given. What about time per due? Not given. Calculate them. Calculate what is volt per due, what is time per due. What we know? We know a formula. I am writing the formula. Peak to peak voltage is peak to peak vertical divisions, in short form I am writing, multiplied by volt per due. Is it not? So what is volt per due from this? Volt per due is peak to peak voltage by peak to peak vertical divisions. How much is peak to peak voltage? Given here 5 volts. How much is peak to peak vertical divisions? Observe from the given diagram, 2 divisions. 5 by 2 is 2.5 volt per due. While observing that given diagram, directly you can do, just doing step by step for you. So volt per due, which is not given in the question, I calculated using the given data of statement 1. And similarly, you please calculate time per due. What is the formula relating time per due? Time period of the signal can be measured, right, by taking 1 cycle horizontal divisions. 1 cycle horizontal divisions. What is the meaning of that? The number of horizontal divisions occupied by 1 cycle multiplied by time per due. That is the formula, right? So what is time per due? What is time per due? Time period of the signal by 1 cycle horizontal division. What is the time period of the signal? Given, actually they gave frequency, I calculated time period. 1 millisecond is the time period by, what is 1 cycle horizontal divisions? 4, don't count all the horizontal divisions, please. Normally people count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, don't do that. 10 divisions are occupied by 2.5 cycles. 1 cycle is actually occupying how many? That 4 divisions, right? 1 millisecond by how many divisions are occupied? 4, 1 by 4. 1 by 4 is 0.25 millisecond per due. See? So the volt per due is this, time per due is this. But that is not the question. Question is not about volt per due, time per due. This can be a question, please. This can also be a question. I observed such question in gate instrumentation paper. They give all this data. They give you only 1 cycle or 2 cycles, something like that. They will ask you what is vertical sensitivity, horizontal time per due, horizontal dial setting value, sweep setting they will mention, time based setting they will mention. This is what time based setting. But what is question? Question is about, this is over the second statement. You observe second statement. Unknown signal is connected. When lengthy statement, you try to divide into volt per into 2 parts. That is what the second statement. What is second statement? The unknown signal is connected to second channel. This is what the image displayed, right? No data is given, it is unknown. Na? Lower trace. What is the peak to peak voltage of this signal? What is the time period? So how many divisions are occupied here? 1, 2, 3. And how many? 1, 2, 3, 4, 5, 6, 7, 8. 8 divisions, horizontal divisions are occupied by one cycle of the triangular wave. 3 divisions are occupied from peak to peak. Don't count here, please. This is 1/4 cycle. Don't say 2 divisions, 2 vertical divisions are occupied. That is wrong. 3 vertical divisions are occupying peak to peak. Okay, so let's see channel 2 display. What is channel 2 display? Channel 2 display is a lower trace. Channel 2 display is a lower trace, is of a known signal or unknown signal? Unknown signal 2. Unknown channel 2 display now, so I am calling it as unknown signal 2. What is the type of the signal? Type of the waveform is a triangular wave. Some other waveform also can be given. So channel 2 display is lower trace, is of unknown signal which is triangular. So let's see here. This is what? One cycle square wave. Sorry, triangular wave, and I think 1.25. So what is N2? Here to here is one cycle. This is half cycle. So this is up to here is 1.25 cycle. 1.25 cycles. How many horizontal divisions are occupied? Already I counted. Na? 8 divisions are occupied by one cycle. Don't count total divisions. Don't count all. All is always going to be same. 10 divisions now. Why that will change? Fixed screen. The number of cycles occupying horizontal divisions, one cycle of triangular wave is 8 divisions and 3 divisions peak to peak. 3 divisions peak to peak. So here to here is 3 divisions. What is one more parameter given? One more information given is, if the time per due and volt per due on both channels are the same, just now we calculated the volt per due. For channel 1 display we got 2.5 volt per due, 0.25 millisecond per due. So it is same. So 2.5 volt per due. And what is that time per due? 0.25 millisecond per due, which we got using, we solved it, calculated it, using the given data in statement 1 about channel 1 display. Calculate what is that peak to peak voltage of the signal 2? Peak to peak voltage of the signal 2 is what? That is the question. Count the number of vertical divisions from peak to peak. Multiply it with the volt per due. In hurry, don't multiply with 0.25, right? 2.5 volt per due. 3 into 2.5 volt per due is 7.5 volts. Actually got your answer, please. 7.5 volts means it is there in option C. Okay, but let's cross check now. Better time period of the signal 2 also you try to calculate, right? So how to calculate time period? Don't count total divisions. Only 8 divisions are occupied for one cycle, per cycle, one cycle, multiplied with the time per due. How much is time per due? 0.25 millisecond per due. That is 8 by 4 is how much? 2 milliseconds. So 7.5 volts and 2 milliseconds is the answer, please. 7.5 volts is not there in any option. Just for cross checking I calculated. That is anyway 7.5 volts once you get, that is enough, because it is not there in any other option. Just to show you the calculation I have shown. So lengthy statement is there. Try to divide into 2 parts. Based on that and try to analyze. Okay. In an oscilloscope screen, recently I think in 2014 paper they gave this. It seems to be a very simple question. In oscilloscope screen, linear sweep is applied at vertical axis, horizontal axis, horizon, both horizontal and vertical axis. Actually, they gave such question, I accepted, but we don't apply it to an axis. Axis will be formed. Let's analyze. Okay, so what you know, this is the screen of the CRO. Like this screen, please. Just now you have seen screen, 10 division by 8 division screen. Rectangular screen will be there, not the way I have drawn. This is the top edge of the screen. This is the bottom edge of the screen. This is the right side of the screen. This is the left side of the screen. This is what you observe on the front side of the CRO. This is the display section. Lot of details will be there inside. Electron beam will be generated, then accelerated, then focused, then it is going to strike the screen. So for deflection, behind the top side there is a top plate. We call it as vertical deflection plates. Behind this right side there is a plate, we call it as horizontal deflection, HDP, and YDP will be there. This input is known as Y input. This input is known as X input. Whatever signal applied here is known as vertical signal, and whatever signal applied here is known as horizontal signal. So we don't actually apply the signals to the edges of the screen, please. We apply signal to the plate behind the edges. This you call it as a top plate, this you call it as right side plate if you want. So this is what your screen, right? Behind this plates are there. This input is Y signal. What is Y signal? I told you two modes are there. YT mode as well as XY mode. Two modes are there. Either in YT mode or in XY mode, Y signal is always the signal you want to measure. You connect your CRO, that is your measuring instrument, into circuit under test with the help of the probe. Whatever be the signal sensed by the probe will be transmitted via cable. And other side of the cable, you did not in the lab, you connected the other side of the cable to the channel input of the CRO. There will be a vertical amplifier, receives that incoming unknown signal, propagated via vertical amplifier, then goes to delay line, it gets delayed, right? And then is applied to Y input. So Y signal is sensed unknown signal, always, whatever be the mode. Let it be YT mode or XY mode, whatever be the mode, unknown signal is always, question mark signal is always applied. Whichever you want to measure is always applied to the Y input of the CRT. That produces vertical deflection, right? But what kind of signal you are going to apply? That is up to you. What people tell me, in the classroom when I ask, people say sine wave. So you saw sine wave on the screen. It need not be only sine wave. You can apply sine wave, or you can apply DC voltage. You don't apply, sorry, in the questions they may mention apply, but you sense and then it is driven, applied to that Y input, right? DC voltage, or maybe AC plus DC, right? Or it may be a square wave also, or it may be a triangular wave also, any kind of signal. All these kind of signals are unknown signals. Any signal can be applied to the Y input of the CRT. I said it is not applied in the sense that you are not applying, actually driving a signal here. You are not physically applying. You are sensing that signal and it is driven to the Y input. We don't apply unknown signal, right? But what about this X signal? That is a horizontal signal. Question is about that only. Horizontal signal in any mode. Let me write here, in any mode. Unknown signal, vertical signal is always sensed unknown signal. Y signal is always sensed unknown signal in any mode. But X signal depends upon the mode of operation. There are two modes now. One is a YT mode. So in YT mode, YT, Y signal is this. What is the meaning of the T? The T stands for time-based signal, sweep signal, or sawtooth signal. From where you will get that sweep signal? You will get sweep signal not sensed by you, not externally applied by you. Inside in the CRO, in the horizontal section, there is a sweep generator. That sweep generator generates a sweep signal. That sweep signal is applied to X input. Let me write here, sweep signal in what? Which mode? In YT mode. That T stands for this only. Fixed. In YT mode means Y signal can be any unknown signal, and this is going to be sweep signal. That will produce horizontal deflection. That is the purpose of applying a signal to the X input, please. But there is other mode now. What is that other mode? XY mode. Why XY mode is given? If user wants to apply this kind of signal, any signal is applied to Y input now in the same manner. If you want to apply sine wave to the X input, not a sweep signal. DC voltage you want to apply, square wave you want to apply, there is a provision to apply your own signal, known signal, not unknown signal, known signal to the X input via something known as external horizontal input. So let me mention, it can be any known externally applied signal. That is what X stands for. External signal in which mode? In XY mode. Any signal you can apply. That is the meaning of that X. Any signal in the sense what? Maybe DC voltage, or maybe AC signal, sine wave, or it can be square wave, anything. That is up to you, please. Any kind of signal can be applied to that X. What is the question actually? Question is about linear sweep is applied at the linear sweep is applied in XY mode to create actually horizontal axis, right? That is what actually we call it as a time axis. Vertical deflection is provided because of this. So what is the answer for this? It is B. It is applied to horizontal input to produce horizontal reflection. In 2014 gate paper they gave this. The input impedance of a CRO is equivalent to 1 mega ohm resistance in parallel with a 45 picofarad capacitance. If it is used with a compensated 10:1 attenuation probe, the effective input capacitance at the probe tip is. That is how they mention about the input impedance, please. The input side there is a vertical amplifier. So what are the input resistance? No? 1 mega ohm is actually the input resistance of that vertical amplifier. So what are the parameters given? 1 mega ohm resistance in parallel with 45 picofarad capacitance. It is used with a 10:1 attenuated probe, attenuation probe. 10:1, 10:1. That is how they mention. They are asking you what is the effective capacitance at the probe tip. So I am just writing first what is the given data. Input resistance of the CRO is given 1 mega ohm. Input capacitance of CRO is given is 45 picofarad. CRO has this input. And what is that one more data given? You can observe here 10:1 attenuation probe. The probe is 10:1, or you can say 10:1 attenuation probe. Attenuation probe. 10:1. What they are asking you? What is the effective resistance or effective capacitance actually? Okay, we will solve effective resistance is what? Effective capacitance is what? Actually they are asking you effective capacitance only. Yes, only effective capacitance, not effective resistance. What is the value of the effective capacitance? What do you know? You should understand uses of attenuation probe. When you connect a probe into the test circuit, there is a meaning for this 10:1 attenuation probe, please. When you purchase a 10:1 attenuation probe, what they are telling you, 10 means what? When you connect your CRO into test circuit with the help of this 10:1 probe, whatever be the signal sensed by you will be attenuated by 10 times. 10:1 probe meaning is what? Meaning is a 10:1 attenuation probe means the unknown signal voltage will be attenuated by 10 times. Not source voltage, signal voltage. There is nothing like source here. And the effective resistance of the probe is going to be 10 times the input resistance. There is a meaning hidden there. When you study, you will understand. A 10:1 attenuation probe will attenuate the signal by 10 times. It will increase the input resistance by 10 times and it will decrease the input capacitance by 10 times. Right? Input capacitance effective decreases by 10 times. This is the formula we want. Right? Just use this formula, nothing else. What is the input capacitance given? 45 picofarads. Now, you should know this. 45 picofarads by 10 times is 4.5 picofarads. 45 picofarads by 10 is 4.5 picofarads. 0.5 picofarads. Normally what confusion people do, there is a formula for CP is CI by n minus 1, the probe capacitance formula. What is CI given as 45 picofarads, right? By n minus 1, what is the amount of attenuation? 10 minus 1 is 9, 45 by 9 is 5 picofarads. What do you remember? Only the probe resistance, probe capacitance. I mentioned in the beginning, design and usage of the probes. If you remember, no, you study only about design of the probe. and you remember effective capacitance formula is so and so, you just simply use, you will get 5 picofarads, you may tick for 5 picofarads. That is wrong. Ci by n minus 1 is a formula for probe capacitance calculation. Ci by n is a formula for effective capacitance calculation. You should be careful about it. 1 minute. Okay, right? So I will be stopping here. I prepared many other problems also. This is only 1 hour session is given. We'll conclude here. Thank you.